Welcome back. So, in the last class, you learned what a controller is and why a robot needs a controller. You also saw an example of a spring mass damper system, that is a second order linear system. So, today we'll move further with that and we'll understand the behavior of such systems with different parameters and its behavior. Okay, so today we'll begin with response of a second order linear system. So let us continue. So this was the slide that you saw even in the last class. So you saw this is a typical spring mass damper system with, here is your mass, this is your damper with damping constant as B, damping coefficient as B, and spring coefficient, that is K. Okay, so K is nothing but force generated per unit displacement. So the unit could be Newton per meter. Similarly, you have B, that is given by force generated per unit velocity of this system. So it should be meter per second. So the units are accordingly. So you see, these are the two constants that are there that basically determines the behavior of the system. Basically, that also determines the characteristics of this system. So that is also defined by the mass which is there. Okay, it is applied by an external force Ft. You see it is here. And let us say if I have a displacement which is given by xt at any instant of time. Okay, so with no external force, that is with Ft is equal to 0, the system can just be written as, so this goes 0, so it is mx double dot p plus bx dot plus kx. So that becomes your time domain equation, dynamic equation of this spring mass damper system. Okay, this is nothing but a differential equation of second order. Okay, alternatively the same can be written as, you saw it can also be written as x double dot plus 2 xi omega n x dot plus omega n square x is equal to f dash. So I have divided the whole of the equation by m. So effectively f dash is nothing but f divided by m. So that is here. So it is proportional to f. So whatever is the behavior of f that is fed as an input, so f dash also goes in a similar way. So omega n is your square root of k by m, that is known as natural frequency of the system. Xi is given by b by root over km. So that is nothing but damping ratio. Okay, xt specifies the displacement of the block as a function of time. That depends on the block's initial condition also, that is displacement and the velocity. To solve this differential equation, we assumed in the last class x is equal to e to the power st, and the solution, you know now, it depends on its characteristics equation, that is given by ms square plus bs plus k, which has a root of s1 and 2. So that is s12, so it is minus b plus minus root over, this is the discriminant which is here, that is b square minus 4mk root over divided by 2m. So it has something which is under square root, that can go positive, it can be a real value. In case it is negative, it will have complex value. So in that case it becomes minus b plus minus a complex number out here divided by 2m. So whole of this S12 is known as roots of this equation, characteristics equation, and this decides the behavior of this system. Okay, let us begin with different kinds of such system. One such system could be an overdamped system in which B is dominant, that is damping is dominant over the spring stiffness. So the roots are real and unequal. The roots are real and unequal. So in that case, we have no external force. So F becomes equal to 0, and this is your time domain solution of your system, and with b square minus 4am going to be greater than 0, that would result in an overdamped system and it behaves in a sluggish way. Okay, The solution would be of the form xt is equal to c1 e to the power s1t plus c2 e to the power s2t, where s1 and s2 are roots of the characteristics equation. C1 and C2 are the constants which can be found out by initial condition, the boundary condition, that is initial velocity and displacement which was given. While you just pulled it at a distance and just released it so that it can oscillate or it can dampen. Okay, so S1 and 2 are the roots of this characteristics equation. C1, 2 would depend on the initial condition. So yes, let us just take one such example and see the behavior of this system. So for this system, I have assumed m is equal to 1. Units are accordingly in SI system. So if it is 1, it is 1 kg. Similarly, B, that is the damping constant, is 5. Stiffness is 6. Okay, so the characteristics equation can be written as ms square, that is s square, plus bs, that is 5s, and plus k, so it is 6. It is equal to 0. So that goes here. So in the last class you saw why this is called as a characteristics equation. Basically this relates the output by input. So output and input is related by this, and in the denominator you saw this goes. Okay, so if that is real, that is 0, that is a constant which are having some imaginary numbers, so that will basically govern the behavior of the system, and that is the reason it is known as the characteristics equation also. Let us start analyzing this. So what are the roots here which will be known as the poles? That is S1 is -3, S2 is -2. So now the equation which I told, it should be like this. So the time domain solution would look like xt is equal to c1 e to the power -3, one of this will go here, and similarly s2, that is -2, that will go here. So effectively your system time domain solution should look like this. Now C1 and C2 is to be determined. We know the system has started from rest. Okay, initial displacement was given. So first of all, let me just take derivative of this. Taking derivative would give me, in time, it should give me x dot t, which is equal to -3c1 e to the power -3t and -2c2 e to the power -2t. Got it? So I now know time domain solution like this, velocity which is like this, so displacement and velocity. Substituting the initial condition, I know t is equal to 0 at time t is equal to 0. When the block was released, it has a displacement of some unit meter, so 1 meter. Okay, and then x dot 0 is equal to 0, that is initial velocity is 0. Okay, so this is how these two conditions can be put over here and here. Okay, so at t is equal to 0, I just put t is equal to 0 in this and put xt is equal to 1 here. So I'll get one equation, and again x dot 0 is equal to 0, so I'll put again t is equal to 0 in this equation. Okay, and I'll get one equation for x dot t is equal to 0, put it here. Okay, so these two will give me two equations. Okay, this one and this one. Solving these two simultaneous equation, I could extract C1 and C2. So you see I got C1 as -2 and C2 as 3. Okay, these values makes this time domain solution of this complete, this system complete. So I'll put them here, and I got to the motion of the system, which is given by xt is equal to -2 e to the power -3t and +3 e to the power -2t. So this is the time domain solution of my system. So now I can plot this with varying time, and I can see how it is moving over time. So it may oscillate, it may dampen. So I'll see the behavior. Also I know the poles of this system also. So those are given by -3 and -2. So that can also be plotted somewhere. So let us see how to go for it. So I'll start with a simple MATLAB code MATLAB, I assume quite a few of you must be having this MATLAB also with you. Even if you don't have, so Octave is a free software which can run any MATLAB code of this type. So you know displacement is to be plotted against time. So you have equation which is given. So this can even be coded with simple MATLAB code, and you can just plot the results. Okay, you just have to plot x with time. Okay, with the same variables that I'll be taking now. So yes, so this is your system, that is the polynomial of the characteristics equation. It was given as ms square plus bs plus k. Okay, three things were there, so that is put here as I have just created a polynomial with the coefficients which are here. So roots of the polynomial will be stored in the variable which is p over here. So p will have the value. So what value it will have? It will have -3 and -2. Got it? So that goes to p, and I have created two plots. Okay, so one of them will plot p. Okay, so that is the first one, that is nothing but p. P means you have two values. So one of them will plot p, that is in complex plane. So you have real number that goes to one axis, and you also have imaginary number. So imaginary is plotted along here, real number is plotted over here. So you know you have both the roots with -3 and -2. Okay, so both the roots will be somewhere over here in the real number line. So -2 and -3 should be visible somewhere over here. So yes, all the poles are drawn in a complex plane. Okay, so as to analyze your system. This has a special significance, you will come to know now. Okay, so why we are plotting the roots of the characteristics equation in imaginary plane somewhere like this, and what does this signify, and how this can dictate the behavior of your system, you will come to know now. So yes, so with the extents, I have just put the extents so that you can see the range. So whole of the extent is now set. Okay, so that you can see the range of your values clearly. Okay, and I have labeled it along x-axis, along y-axis like this. So these are the two constants. With this, your time domain equation of your displacement varies. So xt is equal to c1 e to the power s1t is here, similarly plus c2 e to the power s2t. So you have all the values of constant c1 and c2 here, whereas s1 and s2 are nothing but that you have stored your polynomial roots in p. So p1 and p2 will tell that. So that goes here. So effectively I am writing the time domain solution of my displacement over here, and this is to be plotted. Okay, so what I have done, I have simply made ti vary from 0 to 5 seconds in a step of 0.1, that is told here. Okay, similar is the way in Python, similar is in Octave. So you can just key in like that. So ti goes like this. So whole of the ti is inserted here and here, and xt array is created. So you get for each value of ti, the system has calculated xt, and xt is stored over here. Now this is to be plotted against ti. So xt against ti. So I have created another plot. So what do I get? There are two plots. So this is the one which is the plot of roots, that is -2 and -3. Origin is here. So this is your imaginary axis. This is your real number line. So you see it has some values in real number line. So you have some values which are here. So these two are the poles, and both the poles are on the negative side in the complex plane. So both the poles, and they are on the real number line, they are not imaginary. Okay, so this is your system which was plotted against time. So you have time which goes here and xt that comes here. So you see, you have released it from a displacement which is 1, and then it gradually comes to 0. So without any oscillation, you see it is an system which is given by roots were real and unequal. So B was dominant. So it was an overdamped system. So it is an overdamped system. It quickly comes to rest. So that is the zero thing. Okay. So this is the behavior of your system for real roots which are on the negative side of in the complex plane. So this is the system. This should govern the system, and this is your actual system, how it is behaving. So just remember this, and we'll compare this with other results that we'll be getting in next system example that I am going to give. Okay. So this is first. Now the second one. So this is a system where you have b square minus 4km less than 0. That means I should see complex conjugates. Complex number roots always appear in conjugates. You know that already. If it is a quadratic equation like your characteristics equation. So those two numbers, those two poles, those are the roots, may be written as lambda plus I mu and lambda minus I mu, where lambda is given by minus b by 2m, and similarly mu may be written as this. Okay, so I have just taken I square is equal to minus 1. Okay, so that is a complex number thing that you already are familiar with. So I'll just put it here, and you substituting that value s1 and s2 to this equation. So what do you get? You can quickly write it as xt is equal to c1 e to the power lambda plus I mu plus c2 e to the power lambda minus I mu into t, and again here also you have t. So this can be taken out as e to the power lambda t, that can be taken out. Okay, and inside you will have c1 e to the power I mu t plus c2 e to the power minus I mu t. So that goes inside. Okay, so now I can substitute the second part of it, this one, e to the power ix is equal to cos x plus I sin x. So if you substitute that once again here, so you can get e to the power lambda t, that is still outside, and c1. So here I'll write it as cos mu t plus I sin mu t. So that comes here, and similarly over here I can write it as plus c2 cos mu t. This time it should be with negative sign here, cos minus mu t, and again you have plus I sin minus mu t. So this can be written like this. Okay, so that comes here, minus mu t, and finally whole of the bracket will come here, and that is it. So if you take all of these commons, you can write it as e to the power lambda t c1 plus c2 cos mu t, that will come here, and plus I c1 minus c2, and you can write sin mu t. Got it? So this is how you can write your system xt. Okay, so that goes exactly like this. So if I again take this as alpha 1 and this as alpha 2, so again you can proceed it like this. So you can write it as xt is equal to exactly like this. Okay, so everything comes here. So whereas alpha 1 and alpha 2 are nothing but c1 plus c2 and I c1 minus c2. They can be obtained from initial position and velocity. So you already know when you have released your block, and at what displacement you have released, what velocity you have imparted. So those initial conditions can be put the way we did it just now in the earlier example, and I can evaluate alpha 1 and alpha 2. Okay, so yes, again I'll assume alpha 1 and alpha 2 as r cos delta and r sin delta. That can lead me to this. So how? I'll tell you once again. So what was that? So you just got xt is equal to e to the power lambda t. Here you see you have r cos delta and cosine mu t plus r sin delta and sin mu t. So that is here. So you see you can bring out your r that goes as e to the power lambda t. Inside what you see, cos delta cos mu t, sin delta sin mu t. So that can be written as cos mu t minus delta. Those are simple trigonometrical substitutions. So you see your system behavior will now be given by this. So this is the time domain solution of this. So if you just square and add your substitution which you made here, so squaring and adding will give you alpha 1 square plus alpha 2 square root over becomes r, and dividing alpha 2 by alpha 1 you can get to this, that is delta is equal to tan inverse alpha 2 by alpha 1. So that is there. So quickly you have obtained your equation for the time dependency of your system. Okay, so you can plot your system now with time. The displacement with time you can obtain from this. That will tell you how is your system behaving. Is it oscillating or what it is doing? You already know how is your roots are. Your roots are nothing but complex conjugates. The motion is oscillatory with exponentially decreasing amplitude. You see, this is a constant. Okay, for any value of lambda, this is a constant, but multiplied over e to the power lambda t, lambda is negative. You see, lambda is negative. So it is exponentially decreasing amplitude. So this basically creates the amplitude. Okay, so that is, you see, it is exponentially decreasing, and this is creating an oscillatory behavior. Okay, with time if you plot, your displacement will behave in cosine manner with some phase over here. So it won't start with exact position where you see the peak, but you see here is you have some delta which is here, which is given by this. So the resulting motion should be oscillatory and exponentially decreasing amplitude towards 0 for negative value of lambda. Lambda is negative, you know that. Okay, for b is equal to 0, that is if at all you substitute b is equal to 0, so this becomes 0. So lambda is 0. So in that case this is purely a constant value and you are left with just cosine oscillations. So your system now is completely oscillatory in nature corresponding to S12, which is just plus minus I mu. So what is this? It is just pure complex numbers. Okay, so it doesn't have any real value, so it is imaginary. Okay, so both the roots are imaginary and they are conjugates. Okay, and you don't have anything, so it is exactly on the real imaginary number line, and you have mu which is given by square root of k by m, that is basically the natural frequency of the system. So you have mu, so that is the angular frequency of cosine. So you see mu was here, and what was mu? So you just substitute b is equal to 0 here, you get to mu. So mu is equal to square root of k by m. That will show the natural frequency of the system with which it will oscillate. So now let us just see how to plot this with the system which is similar to this. So you have your system given by m is equal to 1, b is equal to 1, k is equal to 1. Characteristics equation is given by s square plus s plus 1. Okay. Roots are, you see, it is complex conjugate with real value here and imaginary value here. The motion of the system will be given as xt. Xt is e to the power lambda t. Okay, r e to the power lambda t. You see r is 1 here, so e to the power lambda t. So lambda was minus 1 by 2, that comes here, and plus minus mu. So mu will go here, mu t. So alpha 1 cos mu t plus alpha 2 sin mu t. So mu comes here. So again moving further, so if I take derivative of this, so I should be getting this. You can do it yourself. Okay, so first into derivative of second, so and second into derivative of first will give you this. Okay, so this I have done to just get the position and velocity equation of my system. Okay, and when I substitute the initial condition, that is at time t is equal to 0, x is equal to 1, and similarly for velocity, x dot is equal to 0 at time t is equal to 0, putting these two values in these two equations, I can get alpha 1 is equal to 1 and minus 1 by 2 alpha 1 plus root 3 by 2 alpha 2 is equal to 0. So these are two simultaneous equation I am getting out of these two input equations. Solving this, I also will get alpha 2 as 1 by root 3. Alpha 1 you got here and alpha 2 is here. That makes this system time domain solution complete. So now my system equation will tell xt is equal to e to the power lambda t, alpha 1 and alpha 2 will come here and you get the complete solution. So this is how your system will behave. Okay, so if I can again substitute for those constant, you already know that, so you get to a cosine variation of your equation. So you can directly use those substitution where r is equal to this and delta is equal to this, mu is equal to this. So you know you can write your equation in new form, which is looking like this. So here you see this is your r value that is going to come, and e to the power minus lambda t. Okay, so you have e to the power lambda t, lambda was minus 1 by 2. So r is calculated here, and cosine mu t minus delta. So delta is 5 pi by 6. So this is your system dynamic equation. So xt, this is time domain solution. You can quickly plot this and see its behavior. You already know the roots. Roots are complex conjugates. So let us plot both. You can plot in the complex plane. You can show your poles, where does it lie, and you can also plot the behavior. So now I am doing that. So I am using my MATLAB code once again. So I am defining my system, storing the roots here, storing the real and the imaginary values here, and showing them in the complex plane. Now I am labeling them also here. Again I am defining my system over here for the time variation, how my xt will go. Okay, and I am putting them, plotting them once again here. Okay, and I am labeling it here. So see how my system is behaving. You see I have 0 and 0. So that is coming here. That is your origin. So both the poles are on the negative half of your complex plane, and both are complex conjugates. So whatever is this, exactly same value mirrored like this. And your system, you see this time it is started from here. It is overshooting to some value, overshooting on the other side, and coming back. It is still oscillating, which is not clearly visible here, but it is oscillating and finally reaches to the 0. Okay, so what kind of system you expected here? It is a damped oscillatory nature. You see your system is damped oscillatory, and amplitude every time decreases exponentially. So whatever is the amplitude here, next amplitude at every cycle will be reduced exponentially, and finally that comes to this. Okay, so that is how it behaves. So you now see, again you can compare with your earlier results. So this time you have poles which are in the complex side of it. So you have these two value complex numbers, and they are on the negative side of the complex plane. So negative and complex conjugates system is damped oscillatory behavior. Okay, now let us look the system when it was undamped system. So it is purely oscillatory. You have seen by analysis. So by plot, both the roots are shown here. You only have mu here, that is plus minus side in the complex, mu I and minus mu I. So that comes here. exactly on the imaginary line, you see. So this is your roots. So roots are imaginary this time. Okay, it doesn't have any real value. System is oscillatory. The system is plotted here and you see it is having same amplitude every time. It is not exponentially decreasing amplitude. So based on the roots that lie in the complex plane, you have the system behavior. So roots basically decide the behavior of your system. So as soon as you get your system, you quickly find out the roots of its characteristics equation. You can quickly say how my system is going to behave without further looking at the time domain solution and the plots. Okay, so you can directly tell. So this is the beauty of having such plots. Okay, now let us look the third case when you have real and equal roots, that is a critically damped case. I will tell you what a critically damped thing is. So this time you have b square minus 4km is equal to 0. This time you have repeated roots, s1 is equal to s2, and solution by differential equation you already know. So this is xt is given by this c1 plus c2t e to the power st. S is nothing but s1 and s2 is s, and that is given by minus b by 2m. So that quickly comes here. So you can directly substitute s in this equation, and you already know c1 and c2 can be obtained by taking the derivative of this, that is x and x dot t, and substituting the boundary condition. You can obtain two equations. Solving those two equations, you can quickly get c1 and c2. So c1 and c2 is obtained by the boundary condition, the initial conditions. Okay, so that is this at time t is equal to 0. Okay, so this is the most desirable condition as it is the fastest non-oscillatory response. So the system is not at all oscillatory in any case, and it quickly comes to 0. So this is the behavior you want. You know, what you are doing with all these system, you have commanded your robot to go to a place. Your robot may be a second order system. Okay, in this case, you just command your robot to go to a place and it simply can oscillate and come back to a location, or it can just go to a place and stop there, or it can go to that place very fast and still stop there without oscillating. So this is the case of critically damped case, in which it quickly goes to that place and it stops there. So this is the behavior you want. Okay, most of the time you should be like this. Let us say your system is oscillating. What will happen? You reach to a place and oscillate. So that is very much undesirable, because what you will see, you have commanded to pick a ball from a table, and what it will do? It will simply hit the table, because it will overshoot and come back. It will overshoot on the other side, again overshoot. So it can hit the table, okay, without actually going to the precise location on top of the ball and holding it. It will hit the table. So that is what is strictly undesirable in robotics. So you should either be over damped or you can be critically damped. Critically damped is not always possible. So yes, you can be near to critically damped. Okay, so this is the most desirable condition. This is what should be obtained through various parameter tuning. We'll see tuning later on also. So this is non-oscillatory response. And let us just start with one example once again. So this is m is equal to 1, b is equal to 4, k is equal to 4. Your characteristics equation is like this. Now see the roots. Roots are equal, that is minus 2. And I have made my time domain solution. Okay. Taking derivative of this and substituting the initial boundary condition, okay, I can get two equations, that is c1 is equal to 1 and minus 2 c1 plus c2 is equal to 0. So these two are the simultaneous equations. Solving this, I got c2 is equal to 2. So c1 and c2 both are obtained. So that can now be put here and you get the complete time domain solution. So it is your displacement given over time. It will vary over time like this. Okay, so this is how your system will behave. So you can plot this. You can plot your roots also. roots are nothing but real and equal roots. Okay, so again I am using a similar MATLAB code. Okay, so this is your system polynomial, roots are stored p, so you have taken real and imaginary here, you know already, you should not get any imaginary value here. Okay, and plot your markers, so that is nothing but your roots that can be plotted in complex plane. So this is the first plot, and time, this time I am varying my time from exactly like this. Okay, so your time exactly goes like this, it is from 0 to this. So yes, you see you have xt which is de defined here, it is 1 plus 2t, and you have exponential variation that is defined here. So your xt is defined like this. So the symbol star dot especially say is to multiply the two vector term by term. Okay, so that is the way to program it in MATLAB. So now I'll plot xt versus ti. So ti will vary along x-axis and xt is plotted. Okay, so this will show the behavior of my system with time. Okay, and those are labeled here. So let me just see the system, how does it look like. So you know this time my roots were exactly lying at the same location, and that is real. So and both the values were in the imaginary plane, it was 0, it was purely real, and both were -2, it is shown here. So again it is at the left half side of your complex plane. So it is on the left side, both are equal and real. Okay, and your system is critically damped. So again you remember this. So in this case both are real, left side in the complex plane, and your system is critically damped. Real and equal gives you this case. So this is the fastest non-oscillatory response. So you see, as your damping ratio xi decreases, the poles of the system approach to imaginary axis and the response becomes increasingly oscillatory. Whereas with increasing damping, okay, the response gets sluggish. Okay, so there is a time in between in which you should see a critically damped case. After that it becomes over damped. Okay, so this is the set of behavior that you should see in all these cases. I have given some example to make you understand. So you just have to remember how and where your, in second order system you should see those roots, where does it lie. Okay, so it should lie in the left half side of it, and preferably we would prefer to get this, but if not this, you should be happy with critically damped case, or you should be better having a over damped case, but definitely not an oscillatory nature, and pure oscillatory is definitely very bad. Okay, so it will infinitely keep on oscillating. So those are the undesirable cases. Okay, so yes, let us move ahead now and see how does your system behaves with an external force. So this is what your system is actually. Okay, it is not that it is naturally oscillating by some manner, okay, with its natural characteristics. So that is what we have analyzed now. So how does that affect any external force? So you get to see similar results. So in the cases as discussed, if external force is not equal to 0, the general solution in the first case, when real and unequal roots, you should see a similar result. Only thing that will change here is you will see the term which is here. So apart from the constant which is C1 and C2, this is the additional constant. So you should know x0, you should also know x dat 0, and at that t is equal to 0, you should also know how much is your f, what is the force value. So if you also know the third condition, you can get to the third constant. Okay, so these two will create C1 and C2 variations, whereas this one will directly affect this one, and all the three constants will be calculated using three boundary conditions. Okay, so that is for real and unequal roots. Similarly, for complex roots, You should see similar one, similar equation, okay, with Cp coming here. Okay, again same parameters are required to find out these constants, S1 and S2 being the roots of the characteristics equation. So your system characteristics equation remains the same. Okay, so that is not affected by the external force. So that is why it is external. Okay, and in case of real and equal roots, you see this equation again once again, and this is your Cp. So Cp can be calculated by using all those initial parameters. So yes, Cp can be assumed to be a particular solution for initial condition of F. Okay, so that is with initial condition of F, you can find out the value of Cp in all these. Let us just see few examples. So for real and unequal roots, the equation that we have taken, we started with same one, example 1. I have put it once again over here. M is equal to 1, B is equal to 5, K is equal to 6. Characteristics equation remains the same. So the roots goes here. S1 and S2 will come here. Only thing that has changed is the Cp value. If you relate it with previous one, so Cp can directly come to the other side of the equation. I can write it like this. So this is your Cp value that has come here. Okay, so this becomes your time domain solution. Again, in case of complex roots, again you can write your equation like this. You have lambda plus minus I mu. Okay, so mu term will go here, lambda term will go here. Okay, and Cp comes here, and time domain solution will be like this. So plotting these, you can see the influence of external force and how does your system behave with that external force. Okay, similarly for real and equal roots, M is equal to 1, B is equal to 4, K is equal to 4, roots are equal and they are B square minus 4 AC is equal to 0. In that case, you get to see to this equation. This should be a critically damped case once again. Okay, and then this is your Cp value that comes here, and everything is like this. So now I'll plot all of them. Okay, so this time I am using different way to plot it. I am defining it as a transfer function, the way we discussed in the first class. Okay, so this is your first denominator, that is basically xs, that is the output by fs. So this becomes your transfer function. So xs is the numerator. So numerator you have one only, denominator you see you have fs, output by input. So that is the transfer function. So you see xs by fs, so that should tell you 1 by ms square plus bs plus k. So that basically gives you the transfer function. So now this becomes your numerator, that is your denominator. For numerator you have same values for all the cases, whereas this will change. So that is denominator for the first case, for the second case, and for the third case. So you have three systems. All of these can be plotted together in MATLAB. Okay, I am labeling it like this. So I am plotting all the system together here. So this was the system with real and unequal roots. This is the one. You have complex roots. It is oscillatory in nature. It has overshooted, it has come back, and it is like this. And the third one, which is real and equal roots. So this is the critical condition in which it settles down very fast. So you see you have an external force, and with time it settles to a value. This time it won't settle to a value which is 0. This time it gradually, you were at rest, that is here. This is the step input response. So step was just 1 unit. So you quickly reach to the 1 which is here, and you just overshoot it, came back, ultimately you settle somewhere over 1. For different roots, this is the thing which will basically define your system, and this is the behavior of your system. So these are the MATLAB plots. You can do that yourself also in Octave or maybe in Python. This is what is the performance of your control system. So you can quickly write it as displacement plotted here, and your time varies like this, and you see you have overdamped case for xi greater than 1, underdamped case for xi lying between 0 to 1. Okay, and this is the case which was critically damped case, in which it is equal to xi is equal to 1. Okay, so in that case it is critical time, and in this case system settles to the desired value very quickly. Okay, so this is the fastest non-oscillatory response. So everything can be seen here. So this is the plot of the system. So you already know where does your roots lie. So you can, based on the roots and its location in the complex plane, you can decide how is your system going to behave. So you know how to get the characteristics equation of your system, and you can find out the roots. You can say how is my system. Okay, so that's all for today. In the next class we'll see transfer function approach and state space approach of analyzing your system. We'll also look upon a DC motor model of a robot joint, and we'll discuss further. So yes, that's all for today. Thanks a lot.